Okay, so most of you will be aware that we've been in a joint industry project with Equinor, looking at how we can combine vibration with our power tool to see if we can get any extra efficiency out of the system. So the presentation that follows, we've got an explanation of how the system is constructed and how it works, and some results from the first field trial that we did on Statfjord just a couple of months ago. But first, before, I've got a couple of videos which I'd like to show you that make certain points about what we're doing here. So many of you will be aware of this video. It's famous. It's from the 1940s, and it's the Tacoma Narrows Bridge in Washington State. So this bridge was built, and what we're seeing here is a wind of only 40 miles an hour blowing across the bridge from side to side. And you can see how it's set up these vibrations, and it's amplifying the forces that are coming from the wind due to a process called vortex shedding. So later in the day, this bridge actually fell down due to this wind vibration. Even 80 years after the occurrence, experts are still arguing as to the exact reason why it happened. But the point of showing it is that even small forces, when you set up resonance, can have massive effects on large structures. This video shows a comparison, of vibration against hammering. So hammering on the right, and we're getting about half an inch or an inch per blow, and on the left, vibration being applied. When we pan back, you'll see the machine on the top. It's got a couple of counter-rotating off-center weights that are just applying a vibration, and that's making the pile sink into the sand formation below, overcoming the resistance. So we know that vibrations can free stock objects. So if we can build vibration into our power tool system, can we make it more effective? There's actually nothing novel about putting vibration into BHAs. Some patents were filed as far back as 1940, but it seems as though in practice it hasn't actually been applied in the oil field, even though those ideas are 80 years old. So the little graph there shows you what we're trying to do. We've got a static power tool load, and we're going to superimpose a cyclic load on top of that. Now, some scale trials were done with casing packed with clay around to see if the forces were reduced. And when you applied vibration, we got up to a 25% reduction in pull force to free that fish. Interestingly, it only worked for the higher frequencies. So at 6 hertz or less, there was no effect. 10 hertz was the highest frequency applied, and that gave about a 25% reduction. So does that mean you can pull longer casing sections or have less trips? So that's the challenge. Can we do it? The solution that we've adopted is to tune the BHA to amplify pulsation forces. So pulsation forces are going to come from a pulsation device, and we use the agitator. And we're going to add in there a resonance tool, which is in effect a spring in the BHA below the typhoon spear. So when we say tuned, what we mean is we want it to resonate. So we're going to design the system so the natural frequency of the BHA is the same as the pulsation frequency that's coming from the agitator. If you do this, you can get an amplification of those forces. So typically we would expect something like plus or minus 3 tons from the agitator. But if you look at the little graph on the right, down where my pointer is, where the star is, if you can imagine that as the plus or minus 3 tons from the agitator, if we can get the natural frequency correct, then we can expect an amplification of 4 or 5 times that 3 tons. So somewhere between 12 and 15 tons we would expect. And that's a simple model, but the system is clearly quite complex when you take into account the behavior of the fish itself. And we got an outside company to do some modeling to see how accurately we had to get that frequency matching. So on the left-hand graph there, the natural frequency of the BHA in the model was 17.5 Hertz. And the brown line, the smaller one, which only gives you around 1/3 of the output, is 16 Hertz. So if you're even slightly away from the natural frequency, you do get a drop off in output. So this is our BHA power tool and Typhoon, and below that we have about a 90-foot BHA comprised of the resonance tool, the agitator, and a mass in there, because we need a mass below the resonance tool to give us the correct natural frequency. In this case, it's about 3.5 tons of weight required below the resonance tool. In the trials we ran, we had data logging subs below the Typhoon sphere and between that and the resonance tool, and one above the Typhoon sphere to give us accurate records of the data from the test itself. So the size we've started with is pulling 9 5/8 inside a 13 3/8. The test was with Bayrite settled solids outside the fish. It was on Statfjord A. And the little video there, you can see the resonance tool being lowered through the rotary table. So what we do is we run in the BHA, latch the Typhoon and the power tool as we would normally do that. And then we start to circulate. So we're not pressuring up deadheading against the ALO valve. We're circulating through the system, but there's a nozzle in there which still gives us a back pressure in the power tool. And at the flow rates we chose, we aim to get around 250 tons of jacking force in the power tool. I'll explain why 250 tons in a slide or two. And the results we saw from the data logging subs just below the Typhoon, we got plus or minus 14 tons, so an amplitude of 28 tons, and that was vibrating at 16.5 Hertz. And just above the power tool, that was reduced to plus or minus 4 tons. So most of the force is going into the fish, and only a small amount is vibrating the system above. Now on the rig floor, the offshore guys saw no evidence of vibration at all. And this is a good feature of the power tool, that it isolates those vibrations from the rig floor, so you're not going to see any damage to rig equipment or any objects falling from the derrick. Just to give you a sense of context as to what these forces are equivalent to, 250 tons is the weight of the Statue of Liberty. "28 tons is around about the output of a 747 jet engine at full power. So it's pretty awesome, I think, if you can imagine that jet engine being switched on and off 16.5 times a second. The amount of vibration you get into the fixture that's holding it. And that's what we're doing to the fish downhill. 8 tons is a couple of fully loaded Humvees. So we generated all these. Did it work? And also, how can we demonstrate that it worked? Well, we were pulling a fish with settled bayrite around the outside. And one of the features of pulling a fish like that is that it needs many jacking cycles to pull it fully free. Quite often, after it starts to move, the force stays roughly the same for a number of jacking ops. So we went in with a power tool without the vibration assembly and did 2 jacking operations, and each one was the same at around 360 tons. So that's the red dotted line on the graph at the bottom there. So we knew that the 3rd jacking up would be roughly the same. We went in instead with the instrumented vibration assembly, and if you look at the blue line on the bottom, the left-hand side, we decided in advance that we would vibrate for around 5 minutes and then disconnect the power tool to see what the if the fish had moved and how much it had moved. So I mentioned 250 tons before. Why did we choose that? Well, after we had demonstrated it took 360 tons to pull it statically, we picked a number around 2/3 of that. So we were aiming to get 250 tons. As it happened, with the flow rate we ran, we actually got 230 tons. So we applied 230 tons. We were getting vibration at 16.5 hertz. 5 minutes, we stopped flowing, disconnected the power tool, picked up, and we found that the fish had moved 0.6 of a meter, 2 feet, roughly 2/3 of a stroke. And then we repeated it, and we got roughly the same result, just over 2 feet of movement. And then on the 3rd time, we repeated it again, and you can see there we're holding the vibration for 10 minutes, and you get a horizontal line for about 4 minutes. The fish moved that full stroke in 4 minutes, and then the jacking load gradually dropped off as the vibration alone took over. So there's no more power tool stroke, it had gone its full stroke. So we're getting roughly 1/3 of a load reduction to move the fish with vibration versus no vibration. So that's the result. What we're looking for next is more field trials. We've just had the 1 field trial. We're looking for more field trials, potentially with cemented casing or more with settled bayrite. Ultimately, this is where we want to go with the system, adding resonance to tighten. I think the single field trial we've had so far shows that potentially we can pull longer sections, open hole sections, and possibly bonded cemented casing. Can we pull that more easily? You might expect so, because cement doesn't like fatigue, and the vibration force puts fatigue into the cement bond, and you can imagine that when you have to pull the coupling through cement, the hammering forces would break up the cement more easily than static force. So got quite high hopes that it will help the cemented casing example. So that's all I have at the moment. So if you have any questions, please go ahead.